Good morning, class. This is Mr. Roberts sitting here at Shasta High School. This is complicated because this lesson really, I think, should be done in class with all the students. But we're going to try and make do with the fact that we're not all here. And, So, at the heart of it, if we were to kind of relate this to what we've been doing, we've been talking about exponential functions. And today we're going to look at ways that things can grow, specifically money and savings accounts. And one of them is probably something that, maybe grandma and grandpa might make you an offer or something. I don't know that any banks offer simple interest loans anymore, or simple interest savings accounts. But we're going to compare simple interest with compound interest. That's the main thing. And the compounding thing is complicated because it depends on the number of times that you compound. And you'll learn more about what that means specifically. What does compounding mean? How many compounding events occur in the course of a year, in the course of, a day, a second? Compound. All right, so as we're thinking about these questions today, you don't have a team, it's just you and me, but be asking yourself this: how much money does the account start with when it's open? Okay, so if we think about that, that would be like our 0th term on a sequence, or it would be our y-intercept if we were graphing something. So where does it begin? How does it grow? Okay, so does it grow with a multiplier, right? The multiplier, it could be growing by addition too. It may have a common difference, not a multiplier necessarily. And how is the rate written as a percent? How is the rate written as a decimal? Okay, so 32, saving for college. Suppose you have $1,000 to invest and know 2 investment options. One option offers 8% annual interest rate. Okay, an 8% annual interest rate. You can invest in bonds, which pay 8% simple interest, or put your money in a credit union account, which pays 8% compound interest. Will the option you choose make a difference in the amount of money you earn? Examine the 2 situations below. So first, let's look at the bond with simple interest. So if you invest in bonds, your $1,000 would grow as shown in the table below. It's not it right, it's below. How does the amount of money grow with simple interest? So if we look at this, we can see the amount that we started with in the account. We start with $1,000. That's our initial deposit. And we are told that it's 8% simple interest, right? 8% simple. Well, if I was to grab my calculator, and why not, it's right here, and take the $1,000 and multiply that by 0.08, right? I'm finding 8% of the $1,000, and when I do it, I get $80. So I can see that 8% of this initial investment is $80. And what I observe on this table is every single time I go from year to year, from the first year, at year 1 they add $80, right? At year 2 another $80 is added. At year 3 another $80 is added. So yeah, it is an interest rate and it's a percentage, right? But it's the percentage of the initial amount. So with a simple interest, what's happening is I'm calculating the 8% based on that initial deposit. And then every year after that, they continue to just add another $80, another $80, another $80. So we know this, right? We know what this looks like. This is an it's an arithmetic sequence. Excuse me. Ah, once in a while, you just got to get a fresh sip of coffee. So if I wanted to, I could write this out, right? I'm just going to attempt to write it right now. So yeah, I use the percent once. I use the percent once to calculate what I'm going to be adding each time. So if I was going to say the amount of money in my account, and I'll write it as a arithmetic sequence, I could say T of n is equal to, I have an initial deposit of $1,000, but every single year, right, n is years, every single year I'm going to add 80 more dollars, so it's just plus 80n. And I could flip that, I could write T of n equals 80n plus 1,000. So, but you can see here my 0th term where I start is $1,000, and then every month moving forward, I'm adding 80 bucks. So this is simple interest. You use the percent once and only once to calculate what's going to be added each time in the future. So if this account, if they told me that it paid instead of 8%, they said 11.2%, what that would do is it would change what I'm adding each year. That value 80 would change, but that's pretty much it. So that's simple interest. And in fact, let's go to our friend Desmos. Here's Desmos. And let's go ahead and graph that as a function. So I could say y equals, this time I'll type 80x plus 1,000. Boop. Y equals it. Now, you can see I see none of that here because I need to go to where I can see the 1,000. Wow. You know, let's shift this down a lot. All right. So now I can see at least my initial deposit, and these are a lot of dollars. And then let's stretch out the years. So I'm looking at about 12 years there of growth in this account. Good. Oh, that's interesting. Reverse contrast. Ooh. Oh, that looks like they've changed that. I guess I'll leave that here. So that's one way that we could earn money. Simple interest, 8%. We calculate how much 8% of the initial deposit is, and then we just add that year after year. So another option. This other option is accounts with compound interest. So it says, instead, if you invest your $1,000 in a credit union at 8% compound interest, that is compounded once a year. So the compounding is only happening once each year. Its value would grow as shown at the table at right. It's below, we'll look at it. How is it growing? Explain how compound interest is calculated. Why is there $1,166.40 in your account at the end of the second year? So here is the table for that. And if we look at it, just like in the first year, right, I am adding $80. But then an interesting thing happens. I don't keep adding $80. It's slightly bigger than 160. In fact, it's $6.40 bigger. Right? And then the next year, it's slightly bigger than it was before, right, when we added just the 80. So these numbers are not changing by adding 80 each time. Something else is happening. Now, I suspect, and you're probably thinking the same thing, well, is there a common ratio here? So let's fire up good old TI-84 Plus, and let's look at a value like, well, let's just do the first year, right? So if I take this value, 80, and I divide it by the previous year, I get, okay, so yeah, it's adding $80 the first year plus 80, but if you look at this, I have a multiplier here. So what's happening with this multiplier is I've got the initial amount, $1,000, plus 8% of that $1,000. And when I move forward in time, so let's take that initial investment, $1,000, and let's keep multiplying by this 1.08. Let me go grab that number. There it is. So at year 1, there's the 1080. At year 2, at year 3, you see we're rounding it to the nearest penny, right? At year 4, 5, 6, 7. So what's happening here with this compound interest rate is, this compounded interest is, at the end of each year, not only are we adding 8%, but we're adding 8% of not just the initial balance, but we're adding 8% of our current balance. So this is the idea of compounding, that the interest that I earned in the past is now eligible to earn interest in the future. So we know enough about arithmetic and geometric sequences at this point that I think we can write this sequence. We can write these values as a sequence as well. So I'll still use T of n, but I'm going to say that T of n is equal to my initial deposit of $1,000. And every year that goes by, I don't just add $80. It's not plus 80 n. What I do is I take this balance and I'm going to keep multiplying by 1.08. And I'm going to raise that to the power n, where n is how many years this happens. So if I want to know how much the account is worth at the end of 3 years, if I put 3 in for n, it's going to give me that amount. So let's go back over to Desmos and take a look at how this would contrast with that. So here we've got our simple interest still, right? So let's go ahead and now put in the compounded once each year. So I'm going to go, I'll use y again. Y equals $1,000. Okay. This time we're going to be multiplying it by 1.08 raised to the x power. So, initially it's pretty difficult to see the difference, especially at this scale. But if you do zoom in enough, you do start to see that, oh yeah, it is deviating. And in fact, at the end of that first year, where did everything go? Where did everything go? There it is. At the end of that first year, like if this is the number 1 is right here, right? If I zoom in at year 1, I can see that it's a very small difference. No, at year one, they both got $80. There is no difference on that year. But at year 2, am I wrong? Let me look at this. Oh no, where'd the ninja go? Yeah, it's a very, very small difference. So when we look at year 1, right, they're both at the compound interest is at 1,080, and the simple interest was at the same amount. So on that in that first year, right, it's the same value, dollar value at 1, but then at year 2 it starts to deviate. And if we look at this situation over time, right, it becomes more apparent that the longer the time goes by, that the interest, the account that's earning compound interest is going to be worth more. And in fact, if I zoom out at scale here, it's just not even fair. So I think that's our big story today, is being able to think about simple interest, the fact that we compound the dollar amount that we're going to add each time once, and then from that point on it stays the same and it's an arithmetic sequence, versus this compound interest where we don't calculate it once. What we do is every single time we move forward in time, we keep multiplying by another in this case 1.08. We keep multiplying by 1.08. And our multiplier would be different if we were getting different interest rates. If we were earning 12%, right? If we're earning 12%, it would be 1 plus 0.12. So my multiplier then would be not 1.08, but 1.12. All right, let's finish up with question 33. Well, and if we think about question 33, we've done that already. So in question 33, it says, starting with $1,000, show on one graph how each type of investment, simple and compound, grows over 8 years. Use a different color to graph each situation. What happens to the amount of money during the year? Assume the interest is added at the beginning of a new year. What happens to the amount of money at the start of the next year? So this is kind of it's an interesting idea, because when I show you the graph, right, this graph is not really showing exactly what's happening here, because this curve is not always at play. What's happening is, if we're only adding the money at the start of each new year, for the entire year, it's a flat step, and it only steps up when you hit the new year. So there's this type of function that we have that's called a step function, and basically at the beginning of year 0, the account is worth $1,000, and it stays worth $1,000, and then at the end of that year, it jumps up $80, and then it stays $1,080 for that next year, and at the end of that year, it jumps up. So, unfortunately, Desmos, I haven't played with it. I don't know that Desmos will show a step function very well, but we can at least sketch a kind of an idea of what that would look like. Okay, so this is disappointing, but this is the best I can do right now. So for the first year, right, if I was going to look at the simple interest, it would start at $1,000, and it would stay that $1,000 throughout the entire year. And at the end of that year, I might put an open dot here, meaning that at 1, it's no longer here. At 1 year, it jumps up, and this point is the point that's included. And this account will stay worth this $10,000 or $1,080 for the entire duration of the next year, where it's also an open dot. And at the end of that year, it's going to jump up to another $80, right? And I'll fill this in because now that's how much it's worth. And it's going to stay that value until the end of the next year. So this is what a step function looks like, and it's called that because it looks like a set of steps. Now, if I was to contrast this blue simple interest to compound interest, I'll grab a red pen here. Well, for the first year, they share the exact same spot, right? They're exactly in the same location. But at the end of year 1, when this one steps up, it's slightly higher. And it's not much at first, right? It's just slightly higher. Maybe, I can't remember, like $6. And it stays that way for this entire year. Then we've got our open interval. And then the next year, it jumps up even more. It's even higher than that. So what's happening is, over time, we're going to see the gap between these two steps increase. Now, that kind of helps visualize what's happening, because it really is, if we think about it, it's a sequence, right? If we're just compounding once at the end of each year, or we're adding in the simple interest once at the end of each year, it's not going to be a continuous smooth curve. It's going to be very much gaps in our range values. We're not going to hit all the range values in between. It literally goes for 1,000, and then whoops, it jumps up. So let's just look at what our textbook says about this, and then we'll wrap this up. So the textbook says, this is just reading from question 34. It says, in the previous chapters, you used models to estimate actual behavior. Creating a linear model for scattered data gave you a mathematical way to describe the data and to make predictions. The amount of money in an investment account earning simple or compound interest, such as the situation described in problem 33, can be modeled with a step function. Writing equations for step functions can be very complicated. Oh, maybe that's why I haven't stumbled on it in Desmos. However, we can model step functions with continuous functions. Oh, we are already familiar with. Oh, good. They're going to let us out of this. From now on in this course, we will use continuous functions to model situations unless otherwise indicated. Oh, that's fabulous. I'm so relieved, because what they're telling me is that I can go, instead of having this, they're saying, hey, it's easier and we can think about it like this. Yay. So let's just finish here. I'm available all day today, so if you have questions about this lesson or about the homework set, please give me a call. Please join the class. I will be posting solutions to the homework set for today also, so I hope you take advantage of those. And I look forward to seeing you online and back in the class. It's nice when you're back in the class. Talk to you later.